Okay, hello everyone. So today is our lectures on ADCs, which stands for analog to digital converters, and DACs, which stands for digital to analog converters. This course is pretty much relevant to what we are studying in our microprocessors course, but very relevant to any microelectronics and basic or advanced digital logic design, which basically includes DSPs, which stands for digital signal processors, and FPGAs, which stands for field programmable gate arrays. So it's very, I'll say, kind of a common kind of knowledge relating to communicating or interfacing with the, not communicating, but interfacing with the real world signals. And it's kind of very strong engineering concept to acquire. Okay, so let's carry on. So this is one of the very important slide to understand. So what we are trying to do. So what we are trying to do, we are trying to interface with the nature. So temperature is one parameter out there in nature. Let's say what we are trying to measure. Okay, so and the analog to digital converters help us, basically to acquire the real world data. And in this case, the real world data is temperature. And this is a thermometer. As you can see here. So what it does basically, so you have some sensing element. That's, you just simply need to know that there is some sort of a material or kind of a sensor which is used to convert the temperature property in an environment to a voltage. So this P tat is kind of a voltage which converts. So if the temperature is high, the voltage level here will be high. If the temperature is low, the voltage level here will be low. And it goes into analog to digital converter, and the main principle of a converter is that it converts that voltage into an equivalent number of bits. So here N means the information at the voltage level gets converted into N bits, and basically and the digital side basically makes that N bits available as an output for the designer, for the user, or for any other kind of application needs. So the important thing in the operation of an analog to digital converter is the reference voltage. That this is the input voltage and this is the reference voltage. So the conversion happens with respect to this reference voltage, which is fixed in the design. So it's not coming out of anywhere. Depending on, as I said, what we want to measure, we set a reference voltage accordingly so that we can get the best conversion possible at the output. So that's the basic principle of an analog to digital converter. A device that provides an output that digitally represents the input voltage or current level. So again, this can be over here. It can be you convert this into a current, and from current you can make a voltage by just putting a resistor there. So either way, it's basically the voltage coming into the ADC is primarily a voltage. An ADC has an analog reference voltage or current against which the analog input is compared. So again, in this case, it's all voltages, but this can be what this sentence is saying, that this can be current, and the reference can also be the current levels as well. So basically, the ADC is a divider. That's we will look into it, how these statements, what they mean by that. But simply, an analog to digital converter is basically a divider Depending on the voltage levels, the respective deviation happens, and to get an output code, to get the the respective digital output code at the output. Okay, so here's as you can see there's the input voltage V in. Okay, and so the important thing what you see here is the reference voltage here. Okay, so if the reference voltage divided by 8, um, so 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 it means if if the input voltage is within 0 to um, I'm considering this as 0, but I think this is not 0. 0 is here. So this is Vref by 8. So half at the halfway point of the input voltage, uh, if the input voltage remains, let's say, from 0 volt to whatever less than Vref divided by 8 volts, the output will be 000 code. It will only change when the input voltage goes between this point and Vref divided by 8. So in this window, when the voltage changes, the output will be 001. So similarly here, as you can see here, so it's basically a ladder, and this ladder is it's kind of the number of bits. That's how we get at the output. Okay, so the maximum, as you can see here, is this is the maximum code we can get through that 3-bit analog to digital converter, as an example was shown here. So we will go further down into the more specific details of this, and how it's doing it. So, but again, from this slide, since it's a very important slide to understand that we are trying to acquire a real world analog signal, in this case it's temperature, and we are converting it using an analog to digital converter to the respective digital output. And that analog to digital converter is primarily is a divider. Okay, and that's what you see here. It's divided by Vref divided by 8, and so on and so forth. So another few important, I'll say, keywords, terminologies, that it's a mixed signal device. Whenever you hear the term mixed signal, that means it's a device which can handle analog, which is handling analog and digital signals. So in this case, for the ADC, the analog is the input signal, and digital is what it's produced as an output. Okay, and maybe consider to be a divider, same as the previous slide. Output says input is what fraction of Vref, and that's exactly what we see here, that what fraction of from the reference voltage the input voltage is changing, and based on that we generate the output code, and the output code gets 2 to the power n, and n is the number of bits times g, most of the time is 1, the gain factor. But there are ADCs they have a different gain factor, but we will just consider in this particular lecture slide as the gain factor of 1. And an, as you can see here, is the input voltage divided by the Vref, and that's what basically means by the divider. So it means if the input voltage is equal to Vref, so as you can see, you will get the maximum a kind of binary representation at the output. Okay, but if it's halfway point, you will get the half equivalent as a digital code at the output. Yeah, the rest are analog in the V reference voltage, or it can be IREF, as we discussed before. And as I mentioned, that there are ADCs from National Semiconductor. This is a very good presentation which I found from this quality manufacturer. But not only them, but also other manufacturers, producing ADCs with a gain factor greater than 1. What are the advantages, disadvantages? Will be more specific. It will be more like an analog electronics course. But here we are just trying to cover it, the necessary basics relating to the course we are doing. Okay, so that's another, as you can see, has a very good example what an ADC is. All the key signals are shown here, that this is the analog input, and analog input is with respect to the ground you provide. You have the power, and the reference voltage is over here. The reference voltage is set to 8 volts. So here, if you understand this, you will understand this graph in very easy kind of a technical understanding of that how an analog and digital converter works, and why we call it as a divider. So see, if the input voltage is between 0 to 1 volt, okay, so as you can see here, if the input voltage is between 0 and 1 volt here, so I'm assuming that this is going to be 1 volt, so the output code will be 0 right here, as you can see here. But if the input voltage is between 1 and 2 volts, okay, the output will be 001. So 001 means, so this is between 1 and 2 volts, where the output is 001. And similarly, if the input voltage is between 2 and 3, the output will be this code, so on and so forth. If the input is between 7 and 8 volts, like in this final case, then the output code is going to be 111. Okay, so that's kind of a simplistic kind of a technical details relating to that how the analog to digital converter works. And this is the example using a 3-bit analog to digital conversion as an example to understand. Okay, let's carry on. So this particular block diagram is to basically understand that how the conversion principle works in an ADC. Okay, so how the conversion happens, that the analog signal at the input, the circuitry samples it. So there is a sample circuit. Okay, so what it means by sample. So for example, maybe in the next slide I'll show you this. So that means this means a sample. Okay, so the first thing is that the circuitry samples the signal. Like all these dots are basically the circuit is sampling it. Okay, then the next stage is to hold that sample. Very important point to understand both of these, and combined together we call it as the sample and hold circuitry. Okay, so these two blocks are basically sample and hold circuitry. Sample has been taken, it is held. Why it is held? So that we can do the quantization. Quantization means that we are going to convert the held amplitude into its respective discrete values, discrete in time and amplitude. Okay, and then we encode it to the respective digital signal. So in the simplest possible form, you just think this as one block, sample and hold, which samples analog signals and holds it. Then you quantize it, and then you encode it, and these three blocks basically is all what is required to make an analog signal get converted into the respective digital output. Why convert digital and lose information? So that is a very because as you can see here, the analog signal, for example, we are sampling, and assume that this is analog signal is going like this sine wave. Okay, the sine wave is continuous, but here we are just sampling, and this particular window is the error. It's kind of you see that because this even the signal is changing like this. Signal is changing from this point to this point in a very kind of its own analog nature, but we are quantizing it. We are basically fixing ourselves that in this window, whatever the signal is going to do, our output is going to be the same here on all those ladders. So the question is, why convert this digital and lose information? So the answer to that question is because if we lose information, it means the processing is not going to be correct, or the signal cannot be reproduced in the same way, the way it was captured from the environment. So that is kind of a big, I'll say, engineering, kind of flaw. So this question is very important to understand, and the reason behind that is the Nyquist-Shannon sampling theorem. And I think I did mention you that right in the beginning of the beginning lectures, that if the sampling, this sampling of the signal, let's say this signal, since it's periodic, as you can see here, with the frequency, let's say f, and why I just say f max, because of the Nyquist-Shannon sampling theorem, so that you can understand it. So let's say this periodic signal has a frequency f max. As long as we sample this signal at a sampling rate which is twice the maximum frequency in the signal, we are not losing information. So that's a very important point to understand. It means the most of the signal is reliably captured, and we can reproduce it, in the same or almost near to the same shape as we captured it from the environment. So that is a very important point for all of you to understand, that the Nyquist-Shannon sampling theorem states that if you capture any analog real world signal at a frequency which is twice the maximum frequency in the signal, then it means you are not losing information, and that's what when we select an ADC, it's up to us to determine that what type of a signal we are going to capture. We should know the maximum frequency present in that signal, and based on that, the ADC sampling rate, or the ADC chip which we are going to select, we should select the chip which will provide us the required, which is 2 times the maximum, that you can sample and use that IC in your circuit or design. Okay, that's just to because this was a pretty harmonic signal, like an AC signal you get in your home. But this is a kind of another example of a human voice signal. As you can see here, there are many frequencies present in this human voice signal, and the voice of a human, the maximum frequency in that is 20 kilohertz. So it means to capture human voice, you need to sample the signal at least 40 kilohertz, because 2 times f max. Okay, and that is an example of a composite video signal. Why audio and video I'm referring it to, because that's what most of the time we are dealing with in real world. So that is the reason of I'm not going to, because this is not a course on video signal processing or anything. I like this kind of a very nice the video signal, and the different section of it's been present, been shown here. But I'm just trying to show you here that the video signal is changing, as you can see here, and you can transmit it as an analog signal, and receive on the receiver end as a digital signal, or you can use an analog camera, okay, and convert into and that's basically what happens. But let me, historically, we have analog cameras, and to capture then analog signal, video signals get converted into being digital for further processing of desired needs. So I think that is enough in relation to this particular slide. So what exactly, I think it's already, I mentioned it, but this is a more kind of a, these bullet points are very, good ones to understand. So we are talking about a 3-bit ADC. So 2 to the power 3 is 8 possible output codes. And in this example, if the input voltage is 5.5 volts and the reference voltage is 8 volt as we discussed, then the output code will be 101. And very simple, if you just, because the output is, so you just divide this voltage by 8, and you will see that why we are getting 101. We are getting 101 because the voltage you will find will be between 5 and 6. Okay, so that's how the conversion works. Okay, more bits give better resolution and smaller steps. A lower reference voltage gives smaller steps but can be at the expense of noise. So that is a very important point, another very important point for everyone to understand, that we can, to get more, obviously get more bits mean we get a better resolution, and also increasing the sampling rate will give us better resolution as well. But a lower reference voltage will will help us achieve better resolution because the smaller steps. But then we are going to do that at the expense of capturing noise as well. And what is the reason behind that? Because if we go back here, so let's say that this is our noise level, okay, and we are going to just do a smaller step like this, right? So the thing is, we are very near to the noise. That's what it means, because we are talking about analog input. So depending on your environment, what you want to do, these are very important and powerful concepts. Okay, so let's carry on to the next slide. So in the next slide, least significant bit and most significant bits. I think every one of you already know that. This is just representing a binary number, and this we know this is the least significant bit, which is basically 2 to the power 0, and this is the most significant bit, which is 2 to the power n minus 1. Okay, so and n means the total number of bits here. So for example, if we just discard this dot, so this will be 1 2 3 4 5 6 7 8, so it will become a 1 byte. So 1 byte, it means this will be will go like this. It will be 8 minus 1, so this will be 7 6 5 4 3 2 1 0. So 2 to the power 0, and so on and so forth till 2 to the power 7. So that's basically just showing you that the conversion and the respective information relating to binary values. Very basics. Okay. So and the value of the depends upon the reference voltage, and as I told you before, if the reference voltage is, let's say, 1 volt, so it means, and the resolution is 8, so it means 1 divided by 2 to the power 8. So this is your resolution. So try to understand that. Just divide, for example, divide the number 1 with 2 to the power 8. Why 2 to the power 8? Because we are talking a binary output. This is binary output 8. And you will find the voltage as 3.9062 millivolts. If the reference voltage is let's say in this case, if the reference voltage is 2 volts and your resolution is 12 bits, so if you divide 2 by 2 to the power 12, you will find 488.28 as a microvolt as a resolution, a 1-bit resolution of the conversion, and so on and so forth. For the 4 volts, a 10-bit, if you divide 4 by 2 to the power 10, you will get 3.9062 as your one LSB voltage step, or kind of the resolution in your conversion. So that's what we were, kind of referring it to. These are the steps, and that steps is basically, as we mentioned here, is that we are not capturing the signal. Okay, we are not capturing the signal here, which is potentially constantly changing. So this term, where or these steps is primarily call it as quantization error. Okay, and that's because it's a one least significant bit, and since we are constant in that particular window, so it has a 1 LSB of quantization error, and that's what it means by this particular slide. The magnitude of the error ranges from 0 to 1 least significant bit, or simply say 1 bit. Okay, yeah, but more technically it has to be LSB, because we're not talking about any other bit other than the least bit. Okay, so these steps are basically relating to the very important term called quantization errors when we used ADCs. So now in this slide we will discuss the quantization noise, as we discussed in the previous slide. But the important point here is that the quantization noise is inversely proportional to the ADC resolution. So what it means, that if the ADC resolution goes high, you increase the number of bits, the quantization noise will be smaller. So that's what it means by quantization noise. If the number of bits are lesser, then you have more quantization noise. So they are both inversely proportional. Very important concept, and make sure that you understand it clearly. Ask questions during lab, class, office times, and you will be tested in the exams, quizzes, and so on and so forth. So this is one of the technique used to reduce the 1 LSB error to make it a half LSB by introducing an offset. And as you see here, so this is the offset. So rather than if you compare this from the signal was from here to here, okay, but introducing the offset, you see the signal, now the delta has become lesser. Okay, so that's what it is, half LSB, because we are talking about the least significant bit. This is one of the technique used to reduce the quantization error at the output. Okay, so we are not going to discuss there are several other techniques, but I think this is the least what we are going to discuss in this particular session. So another very important concept is called THD. THD stands for total harmonic distortion. So what it is, you see here, this is a simple harmonic sine wave signal, and if you see this on an analog spectrum analyzer, it's kind of a device. You just Google it and you will see the picture of it, like an oscilloscope. It's an analog spectrum analyzer, and you will see just one, because it has only one frequency, so that's what you will see. Whatever that frequency X is, so it can be in hertz, kilohertz, megahertz, whatever. You will simply see one peak, because this is the phase or the Fourier transform of the signal. And if you want to see the analog spectrum of a square wave, that's what you will see, because these edges, so the significant frequency is this, like from here to here is the significant frequency. This is what you see where the peak is, X is, and this X can be different or similar, doesn't matter. So in this case, assume that the X is the same. So this frequency X is the same as X, so you will see the same peak because of the main frequency of the signal. But these edges these edges contains every other harmonic um, you know out there, but the significant ones you see as the odd harmonics, like three times the frequency, and there, as you can see, the amplitude in the frequency domain will be way lesser compared to the primary frequency in the square wave. But the important point here, that these harmonics are because of these edges. You see this edge, and these edges basically causes these harmonics. So, but when we are doing an analog to digital converter, when we are using an ADC, and we take a fast Fourier or digital fast Fourier transform of it, we will see this harmonic distortion, and that's because of the stepping nature, because of this nature of it. Okay, so that's what it basically, a total harmonic distortion, a very important concept relating to analog to digital converters. So as you mentioned, we introduced offset to reduce one LSB bit to half, and as you can see here, this is basically an ideal kind of analog input respective to the output code for a 3-bit ADC, what we are discussing here, to understand the concept. So ideally the line should go that linear, but that's not, and that's the difference between ideal and the actual is what the offset error is. And here what you see this as an error. Okay, so that is an offset, and that's we try to reduce it to make it half LSB, as we discussed in the previous slide. So signal to noise ratio, I'm pretty sure you guys have done and are familiar with this term in your prior courses, but we are just discussing this here, that this is a pure signal, that but that's never going to happen. It only will even from the signal generators you expect the noise. It totally depends on the environment, how big or small the noise can be. So whatever the signal is analog, the real world signal, it basically carries a noise in it, and that's what it's saying. The actual signal is this, and you add it with the noise, and that's how the noisy signal look like. Okay, that's pretty less noisy, that's what I can say. And as you can see here, this is the Fourier transform. Why I can directly tell, because you see the domain is frequency, not time. So that's why the frequency transform of the signal, and the signal level is pretty high, where the amplitude of the harmonic frequency is. Everything else is basically, we will call it as noise level or noise flow. Okay. So typically the important point here is SNR of an ideal ADC is 6.02 nanovolt plus 1.76 dB. Okay, so to understand that, so let's see here the theoretical maximum SNR for an ADC with full scale sine wave input derives from quantization noise and is defined as 20 log of 2 to the power n is the number of bits minus 1 times square root of 6. That's very much relating to signal processing, but in the conversion and mathematics are relating to that. But I don't expect you to remember this, either this one or that one, but this is kind of the theoretical maximum relating to ADC conversion noise, quantization noise, 6.02 nano plus 1.76 dB. Okay. And this is another very important concept relating to analog to digital conversion. One is called oversampling. The other is called undersampling. So undersampling means you are sampling a signal at a rate less than the maximum frequency in the signal. So that is basically undersampling. Oversampling is that you're sampling it at a way higher sampling rate compared to just simply 2 max. Maybe you're sampling at a 3 max or 4 max, whatever. So what are the advantages? In simple terms, the advantage is that oversampling, which is basically one of the feature of delta sigma or sigma delta, wherever you see a type of ADCs, is that um, that you get a less quantization error and you have a more clear signal in your digital domain. Whereas if you reduce from the Nyquist, which is 2 f max, if you reduce the sampling rate below twice the maximum frequency, it will cause what we call it as aliasing in the signal. So this is aliasing is the term. So actually the peak is here, as you can see here, but because you undersampled it, you see the peak here. So that is the concept is called aliasing. So we don't want to do this. This is so that's why we use anti-aliasing kind of to make sure that in different ways we use anti-aliasing in order to make sure that we capture the signal in the best possible correct way. Okay. So comparing again oversampling to undersampling, in the ADC oversampling, time and frequency domain plots the ADC output correctly represent the input signal, and undersampling, time and frequency domain plots the ADC output resembles a lower frequency. Okay, so that's what it's showing there, at the lower frequency. That the actual it was here, but now we are seeing it here, and that what is called as aliased frequency. So now let's discuss, since we have understood the core basic principles of an ADC. So let's discuss the type of ADCs, even though they are mentioned as kind of 5 ADCs, but the most important one we are going to cover here, and the important features we're going to discuss for flash, SAR, or sigma delta, because these are the very commonly used ADCs in microcontrollers or microprocessors, or other digital or mixed signal system designs. And you can find on this flash, SAR, very common in microcontrollers. The sigma delta, yes, on an advanced microcontroller, and so forth. So let's discuss. But there are other types, as you can see here, dual slope and pipeline. But we are just, as I said, we are just going to focus on these three and just focus on a few important points that how they differ. So when we should use a flash ADC, that we need a speed is we need very high speed conversion rate, when the power consumption is not an issue. So we are not concerned about that how much power it's going to consume for analog to digital conversion. So at that time, then we'll use flash ADC. But if we are concerned about power consumption, then SAR is a very optimum choice compared to even sigma delta. Okay. So when we use SAR ADC, SAR stands for successive approximation resistor. Okay. Medium to high resolution, like 8 to 20 bits, we can use SAR. And sigma delta mostly is 16 onwards. And the sampling rate for the SAR is 5 mega samples per second and under. So low power, small size, again, for power concern, relating to when you want to use SARs. And ADC is basically high resolution, low to medium speed, kind of as I said, in the same domain. But I recall this, I used SAR, sigma delta, not SAR. And I think the conversion rate was it was around it was less than 5 mega samples per second. I think maybe 1 or it was 1.5 when I used a sigma delta, 24-bit sigma delta between 1 and 2 mega samples per second. So yeah, just read through it. High resolution, low to medium speed, no precision external components, simultaneous 50, 60 hertz rejection. Digital filter reduces anti-aliasing and requirements. So building digital filters in the IC. We are not going to discuss conversion methods or yeah. So this is encoding method is important because we have relevant circuit which we will discuss. So thermometer code encoding, successive operation is the successive operation, and oversampling is the technique used for sigma delta ADCs. So oversampling, modulator, digital decimation filter is the technique, encoding technique or method used for these respective ADCs. So make sure that you understand these key differences. Then one we pick flash, SAR or sigma delta, and what are the relevant encoding methods for these ADCs, okay, for your exams, tests, quizzes, assignments. Okay, so we are not going to talk about disadvantages and yeah, so I think these are the size is also because it's getting miniaturized every kind of as we go along in the electronics world. So, but I think yeah, good read for the passionate individuals. But as I said, I think for this particular course, we're just going to focus on 1, 2, 3 type of ADCs, and when we pick it, and what is the encoding method. The rest is just there for you to read and ask questions if there is any for the clarity. So this is a very good graph which I found relating to the ADC architecture versus bits and bandwidth. So as you can see here, this is the sampling per second rate. So when we talk about flash, we are talking about in this particular range, 1 to 10 megabits per second. SAR and also sigma delta, they are also kind of in this kind of window. Kind of a very good pictorial view of what we just discussed in the previous slide, where the dual slope is kind of on the lower side of sampling schemes. Okay, and this is the bits resolution. So so I think it's pretty the color, so here it's 100 hertz, so that's what the dual slope is, and it can go up to 24 bits. That's what you see here, maybe a little higher than that, but 24 bits is the maximum what I have worked with. I work with 10, 12, 16, 18 I work with, and also 24 in my career. Okay, so let's carry on. So here are some of the world's smallest analog to digital converters. Why smallest? Is very relevant to microcontrollers, microelectronics, miniaturization, and these are do not by any means want you to memorize these kind of part numbers. No, it's just to show you that how small it can be. So this LTC, I think LTC Linear Technologies is an 8-bit 20 megahertz ADC from analog devices, and the footprint is only 1.75 the size of an SO8. It's very SO8 is a tiny package, and it's just the approximately 2 times the SO8 is a very small ADC, giving you a resolution of 8 bits and a conversion at 20 megahertz. That is enormous, Cool. Okay, so yeah, another just few examples relating to some of the smallest ADCs out there. Analog Devices is one of the leading, company relating to when it comes to analog electronics. TI is both mixed signals, so digital and analog. From TI, I'm just trying to see the company's name. This is also from TI. And this is for Maxim. Maxim is also a very big company, and S3, I don't know from which this ADC is, but anyhow. So again, as you can see here, the Maximum, TI, and ADI are kind of like very popular big companies manufacturing ICs. So this is kind of the internal workings. So let's understand the internal workings of this SAR and Flash and Sigma Delta or Delta Sigma type of ADCs. So as you can see here, the signal is coming in. You have the reference. You set up your reference voltage. Signal comes in from here. This is your sample and hold, and this, which we all know, is basically an op amp or a comparator. Also, we call it as a difference amplifier, but here primarily used as a comparator so that it can generate fixed amount of voltage here, and this logic is basically the control logic to send the converted digital voltage to the respective output digital shift register. And that's exactly what's happening. Bit 1, bit 0, bit 1, bit 0 is basically how the conversion goes, and the control logic also converts the same information back using a digital to analog converter and making an analog voltage here and making it available so that in the next conversion cycle, the first which was converted becomes available to make it kind of, as I said, difference or a comparator circuit. So this is how basically a SAR ADC kind of the internal workings at a very high level works like. So I do expect you to be able to draw this circuit. Okay, very important. Or if I can ask you in the exams to what is the common blocks in a SAR ADC, so you should be able to produce something like this. Or if I can give you the diagram and with everything, all these text missing, and you should be able to put in the text, write the text in order to showcase your understanding. Ask questions during lab time, office hours, or during the lecture time, or send an email and we can connect at a time of agreement. So there's another very I like this block diagram. There's another SAR ADC. And as you can see here, it's sample and hold, control logic, shift register. So it's basically just rearranging the same thing in a different kind of way. So I found this picture to be quite useful relating to what we are discussing on successive approximation register. And this is again the same thing, but more technical inside. That what happens that we just track and hold or sample and hold the input voltage, and this is the comparator, and the feedback comes in, and then you have your the logic, the SAR logic, and this is your shift pitch register, which goes out the digital output. You convert it back using a DAC, digital analog converter, and make it available to your inverted input. And again, the key aspect here is the reference voltage. So this is how the internal workings of a flash ADC looks like. So a flash ADC is the V in coming in here, and again, as you can see, these op amps are used as comparators. So this over here, the voltage output is going to be 0 and 1, right? And these resistors basically are connected with the reference voltage. So see here, so it means this has a reference, this has the maximum reference voltage, whatever we set, This has lesser compared to this, and because we have different reference at the negative or the inverting input of this operational amplifier, so that's how the resolution, because that's what it means by the resolution is Vref divided by 2 to the power n. So how many n's we have? 1, 2, 3, 4, 5, 6, 7. So that's and the eighth one is basically Vin or Vref. So it's an 8 line to 3 line priority encoder, and that's what you see at the output as a 3-bit output, which we already discussed. It's a 3-bit ADC. Okay, so this is how basically a flash ADC works. Is primarily it compares the two voltages and simply outputs either 0 or 1. That's how every single op-amp, also called operational amplifier, also called difference amplifier, works. So this is its main kind of functioning behavior. Okay? If the analog voltage here is less than the voltage here, the output will be 0. If the analog voltage at the non-inverting input is greater than the inverting, the negative input, it will be 1. Okay, and go to this reference for any further details for any passionate students. So let's carry on. So this is the block diagram or internal function of sigma delta ADC. Okay, and here the important so it's showing for a 1-bit ADC, and you see this the integrator, the integration symbol. Okay, that's how it works. So the block diagram is basically the main signal coming in, gets kind of an integrator. Integrator is basically a summation of a lot of inputs, and then it converts to a 1-bit, which fed back through a DAC to this kind of a also it's a summing of the feedback with the input signal in order to produce the outputs. So this is the first order sigma delta ADC, and this is the second order sigma delta ADC. So as you can see here, for the second order, the feedback after DAC will goes to every stage. Okay, so this is stage 1 and this is stage 2, but the conversion only happened with the DAC. Okay, but this integrator sections gets repeated for every order. I think this high level detail is enough for the sigma delta ADC. It's primarily, I'll say in simple words, sigma delta ADC is basically, you can think of this as a lot of averaging. Okay, that's what sigma delta ADC stands for. And this is one of the functional block diagram. I really like it from I think from analog devices, AD7723. And as you can see here, this is your input. Okay, these are your FIR filters. That's what we learned. Reduce a lot of noise, and then you have your control logic, your reference voltage, and that's your output. And it's I think it was a 16-bit, yeah, DB15. So it will go from DB0 right here to DB15. So you get a 16-bit digital output. So again, a good comparison, and it's for a sigma delta. So this is a sigma delta IC ADC, and these blocks basically. That's why I just put it here to showcase this. And if you just see the hand, just click here, and you can take to the respective reference line, just like this and like this. Okay, so now I think we have learned enough relating to ADC. So let's talk about DACs. So these are the popular type of digital to analog converters. One is called weighted resistor DAC. We'll see how it works. The other is R to R ladder DAC. And the third one is a summing amplifier. If you have done operational amplifiers or analog electronics courses, most likely you are familiar with the summing amplifier term. So let's quickly go through it one by one to understand these important concepts. So this is a weighted resistor DAC, and as you can see here, so what it's doing, it's basically, so this is again, we are doing a 3-bit here. So 2 to the power 0R, 2 to the power 1R, 2 to the power 2R. So what it's doing is whatever bit you close, okay, that respective voltage will get into the inverting section of this op-amp. Okay, so if you close all, so you have more kind of the voltage will be the same as you can, because you see here when you close it, if you close, let's say if you close this one, so you have minus VR. So if all are closed, the voltage will be minus VR, but it will be more current getting into it, and that's will basically converts your this digital information, making it on and off to the respective higher voltage. Okay, so again, so you have up to 8, because it's a 3-bit, 2 to the power 3 is 8 voltage levels at the output. Okay, this is one of the very simple weighted resistor DAC kind of functional block diagram. This is the R to R ladder DAC, and this is the most significant bit. This is the least significant bit, meaning you're just putting in 0 and 1s. This is just, you can think this is as protectors or current amplifiers, current drivers, or buffers, whatever you can name them. So whatever bits get enabled, you get the respective voltage at that point, and because of the voltage applied, we get the respective analog change at the output. But we see here that it's that feedback resistor is very important. Same here as the feedback resistor here, in order to achieve the desired objective for weighted resistor DAC or for a R to R ladder DAC. Okay. And this is the summing amplifier DAC, and it's very simple. You know, these are your bits coming in. This is the least significant bit. This is the most significant bit, and you have your resistor coming in here. So primarily, you're just summing up the voltages and to get the respective analog voltage out. So that's why it's called a summing amplifier. You can call it as a DAC, but also it's used for analog signals as well. You sum up the analog voltages and amplify it at the output. Okay, so these are the 3 basic type of digital to analog converters technique or conversion techniques are. And the other one, as many other as any other discipline, there are many other variations you will find, like in this case delta sigma DAC. But as I said, these are the very common one, the DACs you will find as an IC available for you, and it's important that you understand the most commonly used ICs and the concepts related to them. Okay. Okay, we'll connect in our next lecture. Take care.